And now it's time to do some work. In physics, they define work as how much force is required to move something and how far do you move it. So this pen right here weighs a couple of ounces, and if I lift it by 1 foot, then it would be 2 ounces of force times 1 foot of distance. Or for another example, lift a 6-pound calculus book 2 feet into the air. So it's going to be, the force is 6 pounds. The distance is 2 feet. And that's the work. It's going to be 12. And then the units are called foot-pounds. So it would take 12 foot-pounds of work. And of course, you could change this to a 12-pound book and lift it 1 foot, and you'll get the same answer, 12 foot-pounds of work. So if you're in the metric system, then this would be in, the force would be in newtons, and instead of pounds, the pounds would be newtons, the force would be newtons, and then instead of feet, we'd be using meters. So then it would be Newton meters, which is also known as joules. Okay, but what if this is not constant? So let's say, for example, that as you pick up the book, you're ripping out pages. And you're ripping out pages at a furious rate, so that by the time you've lifted it 2 feet, it's now a 1-pound book. Well, that's going to be less work, at least as far as the lifting. Of course, it might take a lot of work to rip out those pages while you're crying about it at the same time. But anyway, so what if either F or somehow D are not constant? So what if they are actually functions? So for the first example, Hooke's law, also from physics. So if you have a spring, here's a nice coiled up wire, there's my spring. When you first start pushing down on the spring, it does not require very much force, but as you press down, then all this energy is getting bunched up here and it's going to be resisting you more and more. So the more you push down, the more it's going to be pushing up. So it's going to take more and more force. So it's not just going to be a constant force the whole time. So Hooke's law goes like this. So the amount of force required to compress a spring and then let's just say that it's in inches or feet or centimeters or whatever, but X is the length. So the force is going to be some constant times X. So in other words, there's a direct relationship. As the X gets bigger, so here the X is small, and then the X is going to get bigger and bigger, then the force is also going to get bigger. And the K really depends on the spring, because if this is made out of really thin metal, then it's not going to require very much force. But if this was made out of like thick steel, then it would take a lot of force. So for example number 2. And with Hooke's law, you could compress the spring or you could stretch it out, either way. So for example number 2, it takes 5 pounds of force to compress a 20-inch spring down to 15 inches. So this information right here is going to help us find the K. So we would have force equals K times X. So this spring is originally 20 inches. So there's my beautiful little spring right there. And this is 20 inches. Now compress it down. So compress it down until it's 15 inches. So this is what's left. This is 15 inches. That means that it actually got compressed by 5 inches. So the X is 5. And the force is 5 pounds. So in this case, K is going to equal 1. So in this one, the force is equal to just X. Now on to the next part. How much work is required to compress the 20-inch spring down to 8 inches? So basically we would need to have it go the first inch and then do force times distance. Then the next one, force times distance. And then the next one. And the thing is, it's constantly changing. So this should actually be broken up into sub-inches, eighths of inches, and then sixteenths of inches, etc. And then add up all of that work. Well, to add up all of that work, we could also integrate. So integrate the force times the distance. So basically each one of these, that could be a delta x, delta x, delta x. So then we would do the force times the delta x, force times the distance. So this is the force times the distance. Now what are the limits of integration? So at the beginning, when it's still at the top, how far is it compressed it? 0. If it's going to compress it down to 8 inches, that means that it's going to have to compress it all the way down to 8 inches, which means that this part that got compressed was 12 inches. So it's going to go from 0 to 12. Whew. The setup was the hardest part. The integrating is easy. So this is just going to be x squared over 2, evaluated from 0 to 12. And then that's going to be 12 squared over 2 minus 0 because of this. And then that would be 144 divided by 2, which is going to be 72. And then we've got inches and pounds. So this would be in inch pounds, which sounds sort of weird to say because we usually use foot pounds, but anyway, we used inches here. Okay, then on to another exciting example. So for example number 3. So there's this water container and it's the shape of a rectangle. And it's got a 5-foot by 7 foot base. And it's filled with 12 feet of water. So hopefully I can draw this in 3 dimensions-ish. So then I need to make a rectangle back here. And then it goes back like that. Oh, I actually should have made it much taller and not quite as long, because this is supposed to be 5 feet by 7 feet, and then it goes up by 12 feet. Well, just pretend this 7 is a little bit shorter and this 12 is a little bit taller. So this thing is filled with water. It's a lot of water. And then you have to get a pump to pump it out over the top. How much work is required? So how much work is it to pump the water over the top? Of course, it would have been much nicer if the plumbers would have put a little drain plug in the bottom and we could just open it up and let it all go out. But this is a submerged swimming pool and they forgot to put a drain plug, so instead you got to pump it out over the top. So what we're going to do is basically take instead of a delta x, this little piece right here is going to be delta y, and then take a slab of water that is just delta y across, then it's going to go back like this, and then take this slab of water, and of course it would have to go back like this, take this slab of water and figure out how much work it is to take that out. So take that slab and get it out over the top. Well, for one thing, water weighs 62.5 pounds for every cubic foot of it. So if you have 1 foot by 1 foot by 1 foot of water, that's going to weigh 62.5 pounds. So how much force is required for this one layer? So the force would be, well, first of all, if you take this thing right here and multiply by cubic feet, that's going to be the force or the pounds. So how many cubic feet is this? Well, it's 5 going this way, it's 7 going this way, and it's delta y going this way. So that's going to be 5 times 7 times delta y, and then that would be feet times feet times feet, so that's in cubic feet. And then you multiply by 62.5, and its units are pounds per cubic feet. And then the answer would be something in pounds, because the cubic feet are going to cancel. Now that would just be one layer of water. Then we need to do that from the bottom up to the top, or the top down to the bottom. Then add all those up, which is exactly what integrating does, is add up all of those little pieces. So they would all have this, which is going to be 5 times 7 and 62.5. And then the depth. So what I'm imagining is like this is the y-axis, and this right here would be the origin. So that means that the depth is, so this part right here would be y, and this part would be 12 minus y. So for this slab of water right here, we would have to take it out this length right here, and that length is 12 minus y. So the distance is 12 minus y. And then there's also this delta y, which I'll just move to the back, and now it's called dy. And do that from when y is 0 to 12. And by the way, if you get these switched, it just gives you a negative instead of a positive answer, but it'll still be the same number. So this is, let me see, I'm just going to factor out this number. 5 times 7 times 5 times 7 times 62.5, 2187.5. And then what's left is right here, integrate. So the antiderivative of a 12 will be 12y minus y squared over 2. And then that gets evaluated from 0 to 12. So the 2187.5 is already factored out. And then when you put a 12 in there, that would be 12 times 12, so that's 12 squared. And then minus, that would be 12 squared over 2. And when you substitute 0, that's going to be 0 and that's going to be 0, so that's the end of it. So then how much is 2187.5 and then times, I forgot to press times. Why is it not doing it? Times, thank you. Third try. 12 squared. The buttons either aren't working or 1, 2 squared minus 1, 2 squared divided by 2. And that would be a whole lot of work. 157,500, 157,500, and this would be in foot-pounds. Now, on to example number 4, which makes the situation just slightly different, slightly more interesting. So example number 4. There's a 12-pound bucket of water. And it's lifted 20 feet. So this is going to stay constant. We're going to lift it 20 feet, but the rope weighs 0.9 of a pound for every foot of the rope. So how much work is required to accomplish this task? So this is 20 feet off the ground, or perhaps it's down a mine shaft. So this is 20 feet. And then you've got rope, and at some point there's a bucket right here, and it's filled up with water. And then take that bucket and move it from right here to right here, which is going to be a distance of delta y. So measuring from the bottom, so I'd count that as the origin. By the time you get to right there, that's going to be y. And then how much work is done for that little increment right there? Well, no matter what, there's 12 pounds. So there's going to be 12 pounds plus, so the rope weighs 0.9 pounds per foot. So how much rope is there? Well, the rope is going from right here to right there. So that distance. Yes, I realize there would be a little bit more because the rope is not going straight down, but this is not an engineering class, so we don't have to be that picky. So this distance right here is a distance of 20 minus y, because the total is 20 from top to bottom, and then this part is y, so this red part right here is 20 minus y. So that means there's that much rope and it's 0.9 pounds per foot. So we'd have the original 12 pounds of the bucket plus we would have 0.9 times 20 minus y. So 0.9 times 20, that's going to be 18. So it's going to be 12 pounds plus 18 pounds, and then minus a 0.9y. Or in other words, this is going to be 30 minus 0.9y. All right, so this is calculating the force or the total amount of pounds. Then we're going to move that a distance of dy. And then we need to add all of those up, which means integrate. So integrate the 30 minus 0.9y, which is the force, times this little distance dy, and then do that from 0 to 20. Okay, so the antiderivative is going to be 30y minus a 0.9, and then this will be y squared over 2, evaluated from 0 to 20. So that's going to be 30 times 20 minus a 0.9 times 20 squared over 2. And then, God love the 0, contributes nothing. So we've got 30 times 20 minus a 0.9 times 20 squared divided by 2. And it looks like it's not that much work. I thought it would have been a number bigger than that, but it's 420. It's 420. It's 420. And that would be in foot pounds. So one other thing I wanted to do with this one is, what if I didn't use calculus? What if I just estimated it? Like engineers and people that actually make things really do. So at the beginning, so when it's at the bottom, at the beginning, this would be 12 pounds plus, you've got a 20-foot rope. So a 20-foot rope that is 0.9 pounds. So that's going to be 12 plus 18. That means that it's 30 pounds. That's at the bottom. What about at the very top? Well, at the very top, you don't need rope anymore because it's right there. So you could just grab it and you got it. So that means that it's going to be just 12 pounds for the bucket and nothing for the rope. All right, now here's my estimation without using calculus. So my estimation is, if you have the very lightest is 12, the heaviest is 30, and then you average those. So 30 plus 12 divided by 2. So that would be 30, that would be 42 divided by 2 is 21. So as you're lifting it, at the bottom it's 30 pounds, the top it's 12, but the average is 21. And then if you take 21, and this is pounds, and you do that for 20 feet, well, 2 times that is going to be 42, but with a 0 at the end, it should be 420. And the calculus says it's 420.